Hello dear students. So in my last class I was discussing about how we are going to demonstrate the scheme for Russell-Saunders coupling. So there we saw that according to the Hund's rule which has been applied, so the most stable state is that which will have the maximum multiplicity, and for groups of terms with the same multiplicity, that with the largest L value, that is L is the orbital angular momentum value, has its lowest energy. Okay. So, and therefore, so among 3p and 3f and the while comparing the 3p and 3f of ground term, so the 3f has the largest L value and therefore it is considered as a ground term. Okay. So next, so I also explained about microstate. So what is meant by microstate and how we are going to calculate the different microstates. Okay. So the different ways in which the electrons can occupy the orbitals which are specified by the configuration are called as microstates. Okay. So this is what we saw in our previous class, and by using the equation, there are two different types of equations. We can calculate the microstates by using two different equations, where we are going to use the factorial sign. By using the factorial sign, we are going to calculate for D1 configuration. So how much or how many number of microstates can be obtained, and also for D2 configuration how many microstates are obtained. So like that, we calculated and we learnt how we are going to calculate the different microstates. Okay. So this is where we stopped in our previous class, and in this session, so I am going to explain about how we are going to understand the spectroscopic ground state for DN system. Okay. So DN means so it will be D1 and D2, D3 or D5, D6 systems. Okay. So where the D subshell will have the respective electrons present in the outermost shell. Okay. So how many electrons are present? So how we are going to write the spectroscopic ground state for DN system, so that will be understood in this session. Okay. So the ground state can be assigned by using Hund's rule. Okay. So Hund's rule is the main criteria or the condition which we are going to use to assign the ground state for DN system. Okay. So you all know what is meant by Hund's rule. You have studied it in your first PUC and second PUC classes itself. So according to the Hund's rule of maximum multiplicity, so it is a rule which is based on observation of atomic spectra. Okay. So here the observation of atomic spectra is very important. That is because so we are going to understand the Hund's rule based on so how many electrons are there in the ground state, and till what extent those electrons which are present in the ground state are stable, and what happens when radiant energy is made to fall on those electrons. So whether it is going to excite to the higher energy state, and while returning, so how much of energy it is going to emit. So all these observations are made in atomic spectra. So this Hund's rule of maximum multiplicity is a rule which is based on the observation of atomic spectra, and which is used to predict the ground state of an atom or molecule. Okay. So this Hund's rule is used to predict the ground state, even though once after observing the energy in terms of light or radiation energy, so it has to return to its ground state. So in Hund's rule, we are going to predict the ground state of an atom or molecule with one or more open electronic shells. Okay. So this is what we are going to study in Hund's rule. So here, to determine the spectroscopic ground state for DN system, so we are going to use the Hund's rule. Okay. So the terms are placed in order depending on their multiplicity and their spin values. We are also going to consider the spin values, that is S values. So S means spin angular momentum. So as I told in my previous class, so each electron will have its own spin. So it is going to revolve on its own axis. Okay. So for that reason, So we will have a spin angular momentum which has been possessed by each electron. Okay. So the terms are placed in order depending on their multiplicity and their S value, that is a spin angular momentum value. So the most stable state has the largest S value, that means so for those electrons which are more stable in the ground state, it means that so such electron has got largest S value, that means see, you just imagine when a electron or any substance, when it has more spin, so then it will retain, it will have the largest spin angular momentum value. Okay. So that means so when the spin of a electron is more, so that means it has got more stable or most stable state, that electron will have most stable state, and the stability decreases as the spin decreases. Okay. So if the electron has got less spin, if it revolves on its own axis in a slow way, or the spin angular momentum of that particular electron is less, so then it means that so it is less stable. So the ground state therefore possesses most unpaired electron spins because this gives minimum electrostatic repulsion. Okay. So for those electrons which are unpaired, okay, so those possess most unpaired electrons in a orbital or in a subshell. So such a type of unpaired electron spins because this gives minimum electrostatic repulsion. So there will be very less electrostatic repulsion which has been observed between the two electrons which are present. Okay. So thus for a given value of S, the state with highest L value is the most stable. Okay. So that means so to which electron which has got highest orbital angular momentum, that is L. So for electron which possesses highest orbital angular momentum, so will have less value of spin angular momentum, and so such electron which is in the state with the highest L value will be considered as most stable. Okay. The state with the lowest J value, okay, so J value, as I told in my last class, it is a total angular momentum which has possessed by a electron by considering or by adding or by summing up the spin angular momentum and also the orbital angular momentum. Okay. So since these two are possessed by the electron itself, the electron is going to possess spin angular momentum, that is because it has a capacity to spin on its own axis, that means to rotate on its own axis. So that is why it is going to possess a spin angular momentum, and it is if we study the structure of the atom, so definitely the electron has to revolve around the nucleus. Okay. So nucleus is the centermost part of a atom, and the electrons which are going to present around or surrounding the nucleus. So it revolves on its own axis. Just you imagine the solar system. So that is why, so when the electrons revolve around the nucleus, definitely it will possess a orbital angular momentum. Okay. So by considering these two, that is the spin angular momentum and orbital angular momentum, we are going to observe a new angular momentum which is called as a resultant angular momentum. So which is called as a total angular momentum, and it is represented by the symbol G. Okay. So the state with the lowest J value is stable for less than half filled d orbitals. So suppose if the d orbitals is less than half filled, so then the J value is stable. Okay. So the state with the lowest J value will be stable, and highest J value is stable for more than half filled d orbitals. Okay. So this point you have to keep it in your mind. So that is the state with lowest J value is stable for less than half filled. Suppose if the in d orbitals if the electrons are less than half filled, so then the lowest J value is stable. Suppose if in the d orbital, if the shells are filled with more than half filled, then the highest J value is stable. Okay. So, now let us take the examples one by one, so that we will understand. So, how we are going to assign the spectroscopic ground term for DN system. So, now let me consider the first example for D1 system. So, example, so scandium 2 plus, so here, so 2 plus represents the oxidation state, but not the electron count. Okay. So, here since it is a D1 system, so only one electron will be present. So, according to Hund's rule, so it will take this position. Okay. So, the D subshells are dxy, dyz, dxz and dx square minus y square and dz square. Okay. So, in this way, so we are going to assign the electrons in the D subshell. Okay. So, according to the D1 system, so here n will be equals to 3 and L is equals to 2 and m is equals to plus 2. Okay. So, m is the value of microstate and n is the what is called as n. So, n will be the number of spin or the total angular momentum which is going to be possessed, and the microstate will take 4 different values. Okay. So, here, so 4 different values will be assigned for this. So, next what is L? So, L is calculated by using the equation which is which we studied in our previous class, that is L will be calculated by counting out counting or by summing up of the vectorial orbital angular momentum, that is L1 plus L2. Okay. So, by adding L1 plus L2, so we are going to get the total angular momentum or the L value, which is called as the orbital angular momentum. Okay. So, here L is equals to 2 and it will have the spin of 1 by 2. Okay. And suppose if it is 2s plus 1, so then it will have 2 into half plus 1, which is equals to 2. Okay. So, next is so what is J value? So, J is equals to L plus S, that is J is the resultant angular momentum, or it is the sum of orbital angular momentum and spin angular momentum. So, we are going to sum up the orbital angular momentum and spin angular momentum, that is 2 plus 1 by 2, which is equals to 5 divided by 2. So, J is equals to L minus S, which is equals to 2 minus 1. 2 minus half, which is equals to 3 divided by 2. Okay. So, these are the two possible J values which we can get. Okay. So, according to the introduction what we studied here, so the lowest value will have more stable state. Okay. So, we will have the lowest value as more stable. So, that is why we are going to write the ground term of D1 system as 2D 3 by 2. Okay. So, this is how we are going to represent the ground term of D1 system. Okay. So, here, so 2 is the value of a spin. Okay. So, here S is equals to 2. So, here we are going to write the spin, and here we are going to write the J value. J is 3 by 2. Okay. So, this is what we studied. So, while representing how we are going to represent the term symbol, see here. So, the term symbol is represented as L. So, here spin multiplicity is written, that is 2s plus 1, spin angular momentum is written, and here the total angular momentum or the resultant angular momentum is written. So, in the same way we are going to write it here. So, here the value of 2 represents the spin S value, and 3 by 2 is the J value. Okay. So, this is how we are going to write the ground term. So, next example is let us consider 3D2 system. Okay. So, for 3D2 system, so here, so there will be 2 electrons which will be present in the D shell. So, the orbital angular momentum is calculated by the vectorial addition of individual orbital angular momentum of each electron. So, that is L1 plus L2, which is equals to 2 plus 1, which will be equals to 3. Okay. So, here the value of L is 3. Okay. So, see here I have not written L. So, L will have, so how much of D value we are going to get, means what is the value of D. So, that will be represented in terms of a term symbol. Okay. So, you go back and see this table. So, suppose if the value is 2, then we will use the term letter D. If the L value is 3, then we will use the term letter F. If the L value is 4, then we will use the term letter G. Okay. So, in this way, so we are going to assign the ground term. Okay. So, similarly, so in this we have calculated the orbital angular momentum, and next is spin we have to calculate. So, for this the spin value will be 1, and for L which is equals to 3, the term symbol which is used is F. Okay. So, spin multiplicity is equals to 2s plus 1. Now, you see what and all the j values can be assigned. So, the values of j is 4, 3, 2. Okay. So, here since this is a half filled, less than half filled, so here also we have to use the lowest j value which will be more stable. So, that is why I am going to represent it as so here the spin will be considered as 3. Okay. So, here the spin which has been calculated is equals to 2s plus 1 is equals to 3. So, 3 will be more stable. So, 3f2 is the ground term which is considered for 3d2 ion system. Okay. And the next example is for D5 system. Okay. So, D5 system means example is magnesium 2 plus manganese 2 plus Mn 2 plus. So, here it will have 5 electrons which is present, and according to the Hund's rule, so all the subshells of d orbital will be filled. Okay. So, all the subshells will be filled, and I will have the L value which will be equal to 6. Okay. So, I am going to get the L value which is equals to 0, sorry, L value which will be equals to 0, and the spin multiplicity, that is 2s plus 1 will be equals to 6. So, now I am going to calculate the resultant angular momentum, which is the value of j. Okay. So, the j value will have 5 by 2. 5 by 2 is the j value. How I am going to get the j value is by summing up the orbital angular momentum. So, here orbital angular momentum is 0 plus s is equals to 0 plus 5 by 2. Okay. So, 5 by 2, which will be written in terms of ground term is 6s 5 by 2. So, this is how we are going to write the spectroscopic ground term for D5 system. Okay. And next example is for D8 system. So, the example for D8 system is so nickel 2 plus. So, D8 system means here 8 electrons are present in the d orbital. So, there, so the 8 electrons will take this part. Okay. So, in this way it will going to get arranged according to the Hund's rule. So, here we have to calculate again the L value. Okay. So, L will take the value of 3, and I am going to calculate the spin angular momentum. So, it will have the two values which will result in the value of 1, and for L is equals to 3, suppose L is equals to 3, then the term which we are going to use is F. So, now we have to sum up, we have to add the orbital angular momentum along with the spin angular momentum, which will give the j value. Okay. So, by using that j value, so I am going to write or I am going to calculate it as I will get 4. Okay. So, here the value is missing. So, you just go through in your textbook. So, since this is more than half filled, so here more than half filled or it is completely filled. So, in this example also, so in this example also, since it is more than half filled, so we are going to use the highest value. Okay. So, here the highest value is 4. Okay. So, if you see it in your textbook, so you will understand. So, since it is more than half filled, so the stable state is 4. Therefore, the ground term is 3f4. Okay. So, the ground term for a different DN system. So, this is a table, that is a table 3. So, this gives the information about the ground term for Dn configuration. So, n will be so D1, D2, D3, D4, D5, D6, D7. So, how the distribution of electrons are going to take place according to the Hund's rule is seen here. Okay. So, this is less than half filled and this will be more than half filled. So, what will be the resultant orbital angular momentum value is given in this column, and what will be the spin angular momentum is given here, and the total angular momentum, that is J value, is represented in this column. So, what will be the ground term? So, how we are going to assign the ground term? So, that is given in this column, and these are the examples. Okay. So, if you go through this table, you will get all the informations of spectroscopic ground term of different DN systems. Okay. So, this question might be asked for 2 marks. So, what is the spectroscopic ground term of D3 and D6 system, or D4 and D7 system? Just you have to write the ground term value. Okay. So, this value you have to write. So, that is enough. Suppose if it is asked for more than 2 marks, that is 4 marks or 5 marks, then you have to calculate it. You have to write how you are going to assign the electrons according to the Hund's rule. Then you have to calculate the orbital angular momentum value, that is L value, how you are going to calculate L value, and the spin value. So, how many spin does that electron can take place, and in terms of that we are going to calculate the spin multiplicity, which will be calculated using 2s plus 1 equation, and then resultant angular momentum, that is J value. So, J value is given by summing up L plus S, that is orbital angular momentum plus spin angular momentum. If you add it, you will get J value. Okay. And then by considering the J value, you have to observe whether it is less than half filled or it is more than half filled. Suppose if it is less than half filled, then the lower J value is used, because the lowest J value will be more stable for less than half filled orbitals or electrons. Suppose if it is more than half filled, then the highest J value is used, because highest J value is more stable. Okay. So, all this has to be answered. So, next what we have to understand here is terms generated by ligands. So, the terms generated from free metal ions have been discussed in the previous topics. Okay. So, these are all free metal ions which we have discussed. So, the ligand field in a metal complex influence the Russell-Saunders coupling. So, the degeneracy of the ground terms are lifted by ligand fields and a number of component terms is used. Okay. So, in addition to the spin multiplicity, so each of ground terms of the Dn metal ions has an orbital multiplicity of 2l plus 1. So, here the splitting of spectral terms of Dn configuration in an octahedral field and tetrahedral field is given in this table. Okay. So, how the degeneracy is going to happen? Okay. So, degeneracy means so from the higher energy state to lower energy state while returning. So, how means which and all the orbitals it is going to take or the electron will occupy. So, how it is going to return to its original state. So, all this will be studied in terms of degeneracy. So, the terms arising from Dn configuration in octahedral and tetrahedral ligand fields is summarized in this table 4. So, here if the term is yes, then degeneracy is 1, and the terms which is used is A1, and next is if it is P, so then degeneracy is 3. So, T1, D means 5, F means 7. So, this is how the terms are used. So, these terms are called as Mulliken symbols, and okay. So, these terms, so the symbols which we are going to represent in this way, so they are called as Mulliken symbols, and A is a orbitally non-degenerate term. So, here A means orbitally non-degenerate term, and E is a doubly degenerate term, T is triply degenerate term. Okay. So, for simplicity the grade or G subscripts, so which we are going to use, the G subscripts are omitted in the term symbol of octahedral ligand field. So, in each case the spin multiplicity, which is the same for the component terms as the parent term, is added as the left superscript. Okay. So, this you can see in your textbook. So, example for 3F, suppose 3F is considered as parent term. So, the component terms are 3F2 or 3T2 or 3T1. So, like this, so the component terms are written. Okay. So, this is how we are going to write the terms arising from DN configuration in an octahedral and tetrahedral ligand fields. Okay. So, I am going to stop it here, and in my next class we will see about what are the different types of electronic spectra. So, there are mainly 4 different types of electronic spectra. So, we will see it in detail. So, what is meant by those 4 types of electronic spectra, and what are the selection rules for DD transition. So, all those things will be discussed in my next class. Okay. So, thank you dear students.